Hi, my name is Maddie Howell and I am a PhD student at Monash University. And today I'll be talking about how we can use astroseismology to measure mass loss of low mass evolved stars in the globular cluster M4. So I was using solar-like oscillations, which present themselves as these Gaussian shapes and power spectrums. And from these solar-like oscillations, we can extract two seismic quantities, which is your nu max and delta nu. And these seismic quantities have amazingly been related to stellar characteristics, such as density, and from there, a seismic mass scaling relation has been derived. And this relation can be combined with the Stefan-Boltzmann law to come up with four individual mass relations. So why was I interested in applying astroseismology to globular clusters? Well, globular clusters, or GCs, provide the perfect opportunity to study stellar evolution benchmarks such as mass loss. And this is because of the homogeneity in the star's initial mass, age, and metallicity. GCs also have a large sample of giant evolved stars compared to their counterparts open clusters. So M4 was the perfect target for this study, and that's because it is the closest globular cluster to us, making it relatively bright, but also because it is the only possible GC we can use to seismically study mass loss with the current available photometry. So my aim with the project was to perform astroseismology and get accurate masses for red giant branch stars, red horizontal branch stars, and early asymptotic giant branch stars. And I was using data from Kepler's second mission K2, where half of M4 was observed for roughly 80 days. There has been one previous seismic study on M4 done by Miklio and his team in 2016, where they measured solar-like oscillations for 8K giants. And my aim was to increase this sample size, which I did, where I actually was able to detect solar-like oscillations in 39 giants, and from there determine an integrated mass loss along the red giant branch. So I mentioned that M4 was observed for roughly 80 days, and this is a short observation period relative to Kepler's previous first mission. And unfortunately, we had to cut this down even further due to some bad cadences at the end of the campaign. So this did increase the noise in our light curves. There was also some inherent instrumental noise in the telescope. And an example of this is the 6-hour roll, which equated to a 1 pixel drift in target pixel files. So for these reasons, it was really important to detrend the light curves properly, or to do it as well as we can. And I have shown examples where I started with this pretty poor looking light curve on the left, which was my raw aperture light curve. Then I was able to detrend it to make it a much better looking light curve there on the right. So even after my detrending pipeline, I still noticed that I was getting low signal-to-noise solar-like oscillations in my power spectra. However, as I mentioned, I still got solar-like oscillations for 39 stars, which was pretty amazing. So the next step was calculating masses for each star using those four equations. And from there, I determined the average for each evolutionary phase and compared it to the expected mass, which is shown or represented by that horizontal grey line in the left plot. And as you can see, equation 3 was not only the most accurate, but also the most precise, and this was because it was independent of delta nu. Because of the high noise in my power spectrums, it made it really difficult to estimate delta nu from the methods I was using, and that meant it was the most imprecise parameter in my study. So it was good that that was represented in the results as well. So mass loss results. By taking the average mass on the red giant branch, or the difference between the average mass on the red giant branch and the mean mass on the red horizontal branch using equation 3, I found an integrated mass loss on the red giant branch to be 0.17 solar masses. And this is consistent with what we expected of a 0.2 solar mass loss, which was found from previous models. So quickly, this study is the largest seismic analysis of globular cluster stars to date, where in my preliminary results, I was able to detect solar-like oscillations in 39 stars. From that, I found a red giant branch mass loss consistent with what we expected from previous studies. And another bonus of this work was we had the first detection of solar-like oscillations in globular cluster early asymptotic giant branch stars. So due to the high potential in my preliminary results, I am working to improve this study further, and I've actually increased my sample size to 89 stars, which you can see in my color magnitude diagram there on the right. And hopefully I will have a paper released on this study later in the year. Thank you.